Welcome back to the deep dive. Today we're jumping straight into some advanced uncertainty quantification, or UQ, specifically this interesting paper on the Residual Bayesian Attention framework, RBA.
Right. And it's timely because getting principled UQ into modern deep learning, especially these big transformer models everyone uses, it's hit some real engineering walls.
What kind of walls are we talking about?
Well, there are really three core challenges people have been grappling with. First, how do you actually make the attention mechanism itself probabilistic? Second, you've got all those residual connections stacking up. How does uncertainty flow through that without just blowing up or vanishing?
Okay, that makes sense.
And third, the really tricky one.
Yeah.
How do you properly pull apart the different kinds of uncertainty? Separating the model's own lack of knowledge, that's epistemic uncertainty, from the noise that's just inherent in the data itself, the aleatoric part.
Got it. So the ambition here isn't just some UQ, it's about building a genuinely unified system, something end-to-end within the transformer architecture that tackles all three of those problems together.
Exactly. That's what the RBA paper proposes, a framework with these three core components, all designed to work together for fully probabilistic inference.
It sounds like a significant engineering effort, because as you said, just bolting Bayesian methods onto transformers wasn't quite working.
Well, people have tried hybrid approaches, sure. Things like scalable variational Gaussian processes exist. But getting those mature Bayesian techniques to play nicely with the standard transformer building blocks, especially handling uncertainty and attention and those residual paths, yeah, that was a big unsolved piece RBA is going after. It's aiming for mathematical consistency end to end.
Okay, let's break down this RBA architecture then. You mentioned three pillars, essentially probabilistic versions of standard transformer parts.
That's a good way to put it. Three key components. First up, you have Bayesian feedforward layers. Their job is basically setting up how parameter uncertainty gets propagated in a differentiable way.
Okay, parameter uncertainty, what's second?
Second is the multi-layer residual Bayesian attention. This is maybe the most novel part, integrating Gaussian process ideas, specifically RBF kernels, right into the attention scores. Plus, it handles those residual connections probabilistically.
RBF kernels and attention, interesting. And the third piece?
The third is the Bayesian covariance construction module. Think of it as the final output stage. It takes everything that's been calculated and makes sure the final uncertainty prediction, the covariance matrix, is mathematically sound, like a proper Gaussian process output.
Right, let's dig into that first one, the Bayesian feedforward layers. So instead of fixed weights and biases, everything's a distribution.
Precisely. This is where the explicit modeling of parameter uncertainty, the epistemic part, happens. They move from deterministic numbers to probability distributions, means, and variances for all the weights and biases.
How do they set that up?
The technique is variational inference. They define these approximate posterior distributions, Q theta, for all the parameters, and typically these are just modeled as Gaussians.
Okay, but training that,
Right.
getting gradients through random samples sounds like a headache. That's where the reparameterization trick comes in, I assume.
Exactly. It's crucial. The reparameterization trick lets them separate the randomness, the epsilon, from the parameters they need to optimize, the mean and variance of the variational distribution.
So you can just use standard backprop.
You got it. It makes the whole thing differentiable and lets them optimize using standard gradient descent methods. Otherwise, calculating those gradients would be intractable.
Makes sense. But neural networks aren't just linear operations. What happens when you hit something like a GELU activation? That usually messes up nice analytical uncertainty propagation.
Right. Nonlinearities are always a challenge. And this is where RBA makes a practical choice to keep things fast. They use the delta method approximation. It allows them to estimate how the mean and variance propagate through functions like GALU analytically, layer by layer.
An approximation, but a necessary one for speed.
Exactly. It avoids needing expensive Monte Carlo sampling at every single activation, which would just grind things to a halt in a deep network. It's a trade-off for tractability.
Okay, and what about the residual connections within this feed-forward block? Are those approximated too?
Actually, no, that part stays analytical. Since the input X and the output of the feed-forward part Fx are both modeled as Gaussian, adding them together in the residual connection is straightforward. The result is just another Gaussian where you sum the means and sum the covariances. Nice and clean.
So it keeps the speed up there too. And the whole layer is trained under the ELBO framework, the evidence lower bound.
Yes. The ELBO objective function does two things. It pushes the model to reconstruct the data well, minimizing that error, but it also includes a KL divergence term. That term regularizes the learned parameter distributions, keeping them close to their prior assumptions.
And how does that ELBO optimization connect to the final uncertainty calculation flowing out of this layer?
The key output, mathematically, is the Jacobian matrix. The ELBO optimization determines the parameters of the distributions, and the Jacobian then tells you how sensitive the output is to changes in the input's expectation. It essentially quantifies how the input uncertainty, combined with the parameter uncertainty learned via ELBO, propagates through this feed-forward block.
Okay, that covers how parameter uncertainty gets handled. Now, the second pillar, multi-layer residual Bayesian attention. This sounds like where the sequence modeling aspect really gets a probabilistic treatment, shifting from just similarity scores to probabilistic correlation.
That's the core idea. It's a significant shift. Instead of just calculating attention scores based on dot products between queries and keys, RBA embeds radial basis function RBF kernels directly into that calculation.
RBF kernels.
Yeah.
Like from Gaussian processes.
Exactly like from Gaussian processes. So effectively, each attention head starts behaving like it has an independent Gaussian process prior. This allows the model to learn potentially complex multi-scale correlation structures between tokens, but in a principled probabilistic way.
Wow, okay. So it's like weaving GP properties right into the attention fabric.
Right.
But you mentioned earlier the problem of uncertainty accumulating or vanishing in deep networks. How does RBA handle uncertainty flowing through the residual paths in these attention layers?
Yeah, that's critical. They don't just add the input and the attention output. They use what they call a Bayesian residual mechanism. It involves adaptive residual weights.
Adaptive weights.
Yes, and crucially, these weights themselves aren't fixed. They're modeled probabilistically using beta distributions.
Beta distributions, why beta?
Because the beta distribution naturally lives between 0 and 1. It's perfect for modeling weights or proportions. So these probabilistic weights modulate how much of the original input and how much of the attention layer's output gets passed on.
And that helps control the uncertainty flow.
That's the idea. By making these weights probabilistic and learning them, the mechanism helps ensure that the variance propagates correctly through the depth of the network. It directly addresses that common problem of uncertainty either exploding or dying out in very deep models.
So we've got uncertainty from the parameters via the feed-forward layers, and now uncertainty got correlations and structure from this Bayesian attention. Two streams. How do they ensure they combine coherently at the end?
It all comes back to the unified optimization. The overall ELBO objective function is designed to incorporate the variational parameters from both the Bayesian feed-forward layers and this RBF kernelized Bayesian attention mechanism. It's trained end-to-end, forcing the two sources of uncertainty to be consistent within the overall probabilistic model.
Right. Makes sense. Which brings us nicely to the third component, the Bayesian covariance construction module. This sounds less about propagating uncertainty and more about quality control on the final output.
That's a good way to think about it. Its main job is to take all the processed information and construct a final output covariance matrix that actually respects the mathematical rules of Gaussian processes. It doesn't just spit out numbers. It ensures they form a valid kernel.
How does it start building that matrix?
It begins with a basic construction using outer products of the learned representations, but then it enhances this with a dedicated uncertainty matrix.
And this is where that explicit separation of epistemic and aleatoric uncertainty finally happens.
Yes, exactly here. The epistemic part, the uncertainty due to the model parameters, is derived from those Jacobian computations we talked about earlier, tracing how parameter uncertainty flowed through the network.
Okay, that's the model ignorance part. What about the inherent data noise, the aleatoric part?
For that, RBA uses a separate independent prediction head, a small network, let's call it FAVAR, whose only task is to predict the variance, the noise level, at each specific output point. This allows for heteroscedasticity, different noise levels for different inputs.
So you get a combined matrix reflecting both. But you said it needs to be mathematically rigorous. What if the matrix built this way isn't technically a valid covariance matrix?
That's a real possibility in deep learning. So this module performs crucial correction steps. First, simple symmetrization, because covariance matrices must be symmetric.
Okay, easy enough. What else?
The critical step is ensuring positive definiteness. A valid covariance matrix can't have negative eigenvalues.
And how do they enforce that?
They perform an eigenvalue decomposition on the constructed matrix. If they find any eigenvalues that are negative or very close to 0, they replace them with a small positive value, like a numerical stability constant epsilon. Then they reconstruct the matrix.
So they literally fix the matrix on the fly to make sure it's mathematically valid.
Exactly. It guarantees the final output K-final is a proper, positive, definite, symmetric matrix suitable for GP-style interpretation and analysis. It's a key part of this systematic engineering claim.
That really underscores the rigor they were aiming for.
Yeah.
Okay, let's talk validation. How did RBA actually perform? They used a whole suite of metrics, right? Not just accuracy.
Right. Accuracy measured by R-rot is there. But the focus was heavily on UQ quality. They looked at PICP, prediction interval coverage probability. Basically, does the true value fall within the predicted uncertainty range as often as the model claims it should?
So is the model's confidence well calibrated?
Yes. And related to that is pain and prediction interval normalized average width. You want high coverage, PICP, but you also want the uncertainty bands to be narrow, low P&W, to be useful.
Makes sense.
And the last one?
ECE, expected calibration error. Another measure of calibration looking directly at the mismatch between predicted confidence and actual accuracy.
So how did RBA do on, say, typical structured data tasks?
Pretty well, actually. On things like an engineering optimization data set for energy efficiency, it got high accuracy, like R-RON around 0.97, and importantly, good calibration ECE around 0.19. It generally outperformed benchmarks like standard Bayesian deep learning or Monte Carlo dropout.
And time series?
Similar story for time series forecasting, like on a household power data set.
Yeah.
Good R-RON around 0.92, but also really good uncertainty bandwidth. PIM-INAU was quite low at 0.18, so it seemed to balance accuracy and UQ quality effectively on these kinds of moderately complex structured problems.
What do the ablation studies show? Did removing parts of RBA reveal anything interesting? Oh, definitely. The most striking result was when they removed the Bayesian attention mechanism. That caused a huge drop in performance, especially in the UQ metrics, but also R took a big hit, dropping way down on datasets like California housing.
So that confirms its importance.
It strongly suggests that the Bayesian attention isn't just a nice-to-have feature, it's acting as a critical pathway for propagating uncertainty through the deep network in this specific RBA architecture. Taking it out really breaks the system's ability to quantify uncertainty properly.
Okay, now for the really fascinating part where it didn't work, the yacht hydrodynamics data set. The performance absolutely tanked, right? Extremely low R, sometimes even negative.
Yes, it was a dramatic failure on that specific dataset. The R values fluctuated wildly and were often terrible, like between -27% and only 3%.
Why would a system that worked well elsewhere just fall apart so badly there? Is RBA flawed?
The paper argues, quite convincingly I think, that it's not really a flaw in RBA itself, but a fundamental limitation related to the data's origin. The physics of yacht hydrodynamics is really complex. It involves strong coupling between different physical effects, and crucially, it has discontinuities.
Discontinuities,
Yeah.
like sudden jumps in behavior.
Exactly. Think about how water flows around a hull. Depending on the speed, represented by the Froude number, the flow regime can abruptly change. The relationship between inputs, like hull shape, speed, and outputs, like resistance, isn't smooth.
And gradient-based models, like transformers underpinning RBA, hate discontinuities.
They fundamentally rely on the function they're trying to learn being reasonably smooth and differentiable. If the underlying physics has sharp jumps or breaks, the model, which learns by following local gradients, can get completely lost. It violates the core assumption.
So the failure on the yacht data isn't RBA being bad, it's RBA highlighting a boundary condition for this entire class of deep learning models.
That's the interpretation. RBA works well when the underlying system has statistical dependencies you can learn and is, moderately nonlinear but fundamentally smooth. When you hit systems with strong discontinuities driven by complex physics, purely data-driven deep learning methods, even sophisticated ones like RBA seem to reach their limit.
That's a really important finding. So, wrapping up, what's the big picture takeaway for someone working in this area?
I'd say RBA itself stands as a strong piece of systematic engineering. It successfully integrates Bayesian principles into transformers to handle those key UQ challenges: attention, residuals, decoupling uncertainty, achieving a good balance of performance, UQ quality, and computational feasibility for many common sequence tasks.
But with a major caveat revealed by the failure case.
Exactly. The yacht hydrodynamics result isn't just a footnote. It clearly delineates the boundary of where current deep learning, purely architectural approaches might struggle. It tells us that for certain kinds of complex physical systems, just building better neural networks might not be enough.
Which points towards
It points towards needing a deeper deeper integration of domain knowledge. We need methods that can combine the learning power of networks like RBA with explicit physical priors, maybe knowledge about where those discontinuities occur or the underlying physical laws. The path forward for those really hard problems might lie beyond pure deep learning architecture innovation and more towards hybrid physics-informed approaches.
A call for integrating domain physics more deeply with machine learning. That's a really provocative thought to end on. Thanks for walking us through this complex framework and its implications.
My pleasure. It's definitely interesting work with lessons beyond just the architecture itself.
Absolutely. Until next time, keep diving deep.